Hello, this video is about Newton's second law. Now I've written it down first this time because it does go on a bit. So here we go. The rate of change of momentum of a body is directly proportional to the resultant force and takes place in the direction of the force. Okay, so let's analyse this. First of all, let's look at momentum. Okay, momentum is a quantity given by the letter P, and that means P, which is the momentum, is equal to the mass of the body times its velocity. Now momentum is in fact a vector, so it has magnitude as well as direction. Okay, what else do we look at? Let's have a look at rate of change. Now rate of change refers to time. So how does momentum change with respect to time? Okay, where else we have? A body. A body could be anything here, a body. And now that could be anything from an electron to a container ship. Directly proportional. Directly proportional generally means that if you had a graph like that, you would have a line going through the origin like that. That shows direct proportionality and is written as, well, let's say, so rate of change of momentum is directly proportional to the force. So you could write that as, if you like, the force is directly proportional to the rate of change of momentum, which we'll write for now is dp by dt. We'll expand that later, so it's proportional. That's that symbol, it means proportional. To the resultant force, resultant force is, so if you've got, that means resultant means if you've got two forces acting on the object in opposite directions, it is a larger force take away the smaller force. So it is the difference between the forces and takes place in the direction of the force. So that makes sense. So if the resultant force is acting at 30 degrees to the horizontal, therefore the rate of change of momentum is acting at 30 degrees to the horizontal. Okay, now we'll go and look at this law mathematically. So I shall rub this out. Now, so as mentioned earlier, you have momentum. Momentum given by the symbol P is equal to mv. So from Newton's second law, we can say the resultant force, which will give F, is proportional to the rate of change of momentum. So we can write that as d m by dt. So these are instantaneously small changes. Now, this can also be written as F equals a constant. So from the proportionality, we can write F equals a constant multiplied by the rate of change of momentum. Now, in the case of our case, in Newton's second law, K is equal to 1 because the Newton is defined as the force that would accelerate a kilogram by 1 meter second to the minus 2. So by the definitions, the SI definitions, we get K equals 1. So therefore we can write that force is equal to dm dt like that. Now, from here, we can actually get to three formulas, if you like, that can be used. So this is and we will work with that. Now I'm going to rub this off and we're going to leave the bottom on, which is the mathematical expression of Newton's second law, and we'll see what happens. First of all, let's say that the mass is constant. So, for instance, if a ball is accelerating, there's a force on a ball, rather, the mass is constant. So we can write that as, so from here, we can get force equals, we take the mass out, it's a constant, dv dt. Now dv dt, the rate of change in velocity with respect to time, is simply acceleration. So that gives us force is equal to mass times acceleration, which is a very popular and commonly used version of the second law. Okay, another version we can say from here is what is the velocity constant. So if the velocity is constant, we can write it as force equals velocity multiplied by dm dt, which is very useful when you're looking at systems in which the velocity is constant, but there is a change in mass. For instance, rockets, water flow, helicopters use this formula where you've got a change in mass, such as the mass is decreasing by 30 grams per second, and that's another version of it. And another version we can write it is simply the third way of it. Let's keep it like that, so that the force is simply equal to the rate of change of momentum. So we are not splitting that mass and velocity at all, we're just using this force equals dp by dt. Okay. Now with this one here, that is often used for when you have a collisions and crashes and things like that. So for this one here, what you'll find, now I'll rub this out, is you will get things like force is equal to change in momentum divided by time. So very useful for balls hitting walls, car crashes, etc., where you use the momentum in it, and that can be written as mv minus mu divided by time. A very useful equation indeed.